fine. It's not-
Okay,
That's when I said, I'm not.
how did the homework go? Everybody get something in?
Mm,
Yeah.
My next was.
You know, actually second guessing myself.
What's nice is we got the homework in about the pumping lemma just before we do more,
Before we do what?
before we do more of them.
Oh, good.
There were probably a couple lectures out, 1 or 2 lectures out from going over more pumping lemmas. If you'll prove things aren't context free, how are we gonna do it? Not quite there yet. In the meantime, we'll start where we left off last time, talking about this NPDA example. We had a solution that was just a sequence of transitions, but I also kind of want to draw this out so that we get a bit more of a visual representation to again hone in on why it's easier to just work with grammars sometimes. So here were the transitions. So first here was the language. You're recognizing WWR. So some string followed by that string in reverse. We talked a bit about the end of class about non-determinism and about how non-determinism parses this. So it's actually going through in parallel and figuring out and looking at every possible place where we could break into W and WR, where W ends and WR begins. We don't know where that is because we don't know the length of the string when we start. So we just start guessing. We start using multiple threads to start shifting after 1 character, shift after 2 characters, shift after 3 characters. And most of these threads are going to result in failure. But as long as one of the threads finds success, then we accept the string. It's very different from writing an algorithm for that because you would need an infinite source of parallelism. Because we don't know how long the string is going to be. If the string is 1,000 characters long, there are 999 possible middle points in the string as we find it. So we would need to be running many of these in parallel. We wouldn't be running all 999 because some of them would fail before some of them transition to that. But we would need a significant source of parallelism that we just don't have in modern computers. All right, so a little bit too much animation here. Get all these on the screen at once and let's start drawing. Okay, so we have some state Q0 and we need to start thinking about where are the transitions. So we have Q0 and from Q0, we're going to loop to Q0 1, 2, 3, 4, 5, 6 times. And you can draw this as a single loop and give that loop multiple possible edge names or edges, depending on how you want to do this. I'm just drawing this out so that we can visualize each of them to see how many of them there are without counting. It's a little bit more visual to do it that way. So from Q0, we end up in Q0. What do? We want to see that there is an A on the stack and we want to replace it with AA. So we want to push A onto the stack. How did we represent this transition before? How many components were there? Rather than just in a DFA or an NFA, we had a single edge label.
3.
There were 3 components. What were they?
The letter from the string, what you're popping from the stack and what you're pushing onto the stack.
Yeah.
Or I guess the second would be what's on top of the stack.
Yeah, so we are on an A, popping an A, and pushing an AA. So this, and this from the transition. That's not confusing at all. We can also read a B, pop an A, push a BA. So we have B, A, BA. We could have A, B, A, B. We could have B, 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 B. We could have a z, or a lambda. This assumes that the bottom of the stack character is a z. So if we're seeing something like, all right, the z can be there, that's fine. We can also have b, z, b, z. Those are all transitions from Q0 to itself. We need to transition over to a state we're gonna call Q1 that represents. We make this transition whenever we think we might be at the middle of the string. And again, we do that non-deterministically. We're just gonna start moving over every possible place that we can non-deterministically. So this is Q1. Also non-final. So the different ways that we can go from Q0 to Q1, there are two possible paths. One would look at, all right, so we're going to make a lambda transition and make no change to the stack. But the top of the stack character was an A. And on this one, we'll make a lambda transition, doing nothing, but the top of the stack character was a B. So we need separate transitions defined based on every possible top of the stack character. The reason this is, if we just had one of these, then if the other one were the case, we would fail, which we don't want to do. From Q1, we need to start matching against the reverse of the string. So we're going to have two loops from Q1 back to itself. Throw my start arrow that I always forget. So we're going to a lambda. What does that mean?
Yeah, and you'll pop in.
Yeah, an A on the top of the stack will pop an A. Here we have C a B, B's on top of the stack, pop the B. And then we need some way to know that we are done. If after this process completes, we have an empty stack, we can transition to our final state, Q2. And this is done on an empty stack, consuming no input characters. So we just have to recognize that we are at an empty point in the stack. So we can now freely transition to our final state. We can only have an empty stack if we built the stack contents up and then removed exactly those stack contents. There's no way to push from Q1 and there's no way to pop from Q0. Does that make sense? So once we make this transition, we're done adding to the stack. We add to the stack, we remove from the stack, and then we check for empty. And only if we've removed everything that we added from the stack and there are no input characters left to read, can we transition to Q2 and accept. Questions on this, how this set of transitions maps to this visual image? People are having way more fun out there than we're having in here. It's not Monday to them, it's already the weekend.
This weekend, we're on to our fourth Monday.
Recognize not computer science majors, you see them laughing, having fun.
Homework before is on like Monday. Yes. Like, oh, right, Monday.
So the last thing we're gonna really care to do with, well, I guess there are a couple more things we want to do. The first of those last couple things we want to do with context-free languages is be able to convert from grammars to automata, just like we did with regular languages. We want to be able to take a grammar and say, can we construct an automata from that grammar? So let's start talking about how we might do this. So there is an equivalence between context-free grammars and non-deterministic push-down automata, just like there were between regular grammars, and DFAs or NFAs. Note that this is only non-deterministic pushdown automata. We have not yet talked about deterministic pushdown automata, but they're not equivalent. A non-deterministic pushdown automata is not equivalent to a deterministic pushdown automata. We'll talk about that difference more in a bit when we talk about deterministic context-free languages. But for now, we will need non-determinism in our automata to be able to represent a context-free grammar. We need some way to actually do this, some process for this conversion. The algorithm is pretty straightforward if we make an assumption that the grammar is in Greibach normal form. So this is the main use of Greibach normal form that we are going to talk about. We didn't go into detail about Greibach normal form. We just kind of defined it and then said, this is only used for one thing, so we're not going to study it in detail. This is the one thing. So we're going to study this process. And if on any homework or any exam that you get regarding this process, the grammar will already be in Greibach normal form. The first step of this process is to convert the grammar to Greibach normal form. But since we didn't go over that, you will always get a grammar in Greibach normal form for any problem that is a conversion. So if it's not in what we'll call GNF, we'll have to convert it to GNF, but again, we're not going to do that in this class. We'll just assume that the grammar given is in Greibach normal form. We're then going to do a leftmost derivation of each production in the Greibach normal form, and each one of those productions will define some kind of transition in the associated automata. So as we parse the grammar, because it's in that form, we can immediately link it to the kinds of transitions that we expect in a non-deterministic pushdown automata. So here's a grammar. We have two productions, S to A capital S, B, B, or A. First thing we need to do is convert it into Greibach normal form, which I've just done here. Here's that same grammar in Greibach normal form. So this is the form that you would get if you were to do this problem yourself. Now we have 4 productions, S to lowercase a, capital S to lowercase a, capital A to lowercase b, capital B, and capital B to lowercase b. Let's move forward and see how this process is actually done. So we know that anytime we're going to parse this grammar and create a string that's in the language, or be able to ask the question, is this string in this language? We always start with the start non-terminal. So any derivation that we make with this grammar is going to also start with that start symbol. It gives us a single place to start. So if we're starting our non-deterministic pushdown automata, there's also a start state for that. So we're going to make a mapping between the start state of the automata and the start production of the grammar. Instead of pushing A's and B's or whatever, zeros and ones, whatever we've done before, we're going to have a stack alphabet that is precisely the same as the set of non-terminals in the grammar. And that helps us to know we need to resolve this non-terminal into either any of these possible productions. And the non-terminals again represent variables. So we're going to push the variables onto the stack that we see. And when we resolve a non-terminal, we're going to pop those off of the stack. And so we're using the stack of the NPDA to represent kind of a leftmost derivation of the grammar and all of the unknown variables that we have so far. If that makes sense. So the first rule we want to make is, all right, we're going to go from the start state. We know that we're reading nothing. We have the bottom of the stack symbol is still Z. We need to move to a new state. We'll call it Q1. And I did not subscript these, oops. And we're going to push an S onto the stack. This is just the very first thing that we do. We're going to push that start non-terminal onto the stack, saying that we need to resolve this in some capacity. We don't yet know how we're going to move forward with this, but there are going to be options. Those options will be represented by the non-determinism in the automata. So we need transitions that define each possible way to pop an S off the stack. So we know at the very beginning, we push an S onto the stack, and then we have options for what to do if we're going to pop an S off of the stack, which is the only legal move we can do after we push the S onto the stack. There's no other place that we could start except pop an S off the stack and look at one of these possible productions that utilize it. So the general rule here, the next step, is to look at all productions that are defined by this particular non-terminal and make a rule for each of those. If we pop an S, we can read an A and push an S and an A. Or rather an A and then an S. We can also pop the S and read an A. So those are the two rules we want to be able to make. Yeah,
Repeat the first one that you just said, the how
Yeah.
the A and the S and A gets.
we're gonna read an A from the input string. So all the lowercase letters in the grammar are parts of the string. So we would be able to say if the next character that we could read in the string is an A, then we can pop an S and push this A and then S.
Okay.
So we'd have to resolve the S first, and then after we resolve the S, we can resolve the A.
Right, yeah, cool.
So S arrow, lowercase a, capital S, capital A, read an A from the input, pop the S from the stack. You're gonna pop the left-hand side of the production, and you will push any non-terminals on the right-hand side of the production. S arrow lowercase a means read an A from the input, pop an S from the stack, push nothing, because there are no non-terminals in this production. S arrow lowercase a. So if we're writing these, we could do something like this. So this defines the transition. We read an A from the input. We're in state Q1. We pop an S. We can either push an SA and be in state Q1, or we can just have popped the S, push the SA, pop the S, still be in state Q1. So two possible rules here. I note that there's only one transition here, but because this set contains multiple tuples, it's really defining multiple transitions. So this can lead you here, or this can lead you here. If we were drawing this out, we would have the state Q0 that we had. We have an initial state Q0. We can move to state Q1. When we do this, we're going to lambda z sz. It just says we're not reading anything from the input, but we're pushing an S onto the stack. That's the move from the initial state to Q1. Q1 is going to have two possible transitions. And I'll just draw these, I guess, right here and right here. The first possible transition says we loop from Q1 to Q1, we read an A, we pop an S, and we push an SA. This one says we read an A, we pop an S, and we push nothing. So those are the two possible transitions from Q1 to itself. And that represents both of these productions in this grammar. Questions on the start of the process? We can continue. The next possible production here says we need to read a B, pop an A, and push a B. Do we see how that's embedded within the production? anything in dry block normal form is going to have the terminals first. So we can easily parse the dry block normal form to say, the left-hand side, this is what gets popped. This is what gets read. And any non-terminals at the end, this is what gets pushed. So that's the general dry block normal form. How we're gonna read it, how we're gonna map this form to the following transition. So this says, from state Q1 to state Q1, we're going to read a B, pop an A, push a B. So we need some way to loop from Q1 to itself that is going to read a B, pop an A, and push a B. Here we have another. And now it's all over my diagram. Oops. So this transition says we're going to read a B, pop a capital B, and push nothing because there are no non-terminals on the right-hand side of this production. So we have one more Q1 to Q1 loop that is going to read a B, pop a B, push nothing.
Why are we doing everything only in Q1? Why aren't we creating new states and?
Yeah, so this all happens in what's like a parsing state. So there's no reason for us to move states unless we're moving, the reason we moved states from W to WR is we went from pushing things to the stack to popping things from the stack. It was recognizing W versus recognizing WR. And here, like what if we had something like that didn't just refer back to S? We'd find ourselves back in the same state kind of recursively. And we would want to be in the same state for that. If we move states, we're basically saying that the S that we arrive in here is different from the S that we arrived in here for some reason. And here we just have a single parsing state. And this is, we see this a lot in pushdown automata. If we're not recognizing something that has multiple parts or multiple methods, if you were writing a program to do this, you would want a method for recognizing the W part and a method for recognizing the WR portion. So you'd have separated those scopes. And in this case, we kind of just have one parsing scope for all of these rules, which is kind of gross. And again, why we look at things in grammars rather than pushdown automata. We visualize. Now that said, the pushdown automata is super useful if you're writing a program. A program that doesn't really parse grammars as efficiently as reading through a state machine. So you may want to make a digital representation of this state machine. And if you do, you may want to take an input grammar and produce the appropriate state machine, which is why we want to be able to do both. This is a better digital representation, but yeah, context free. No easy way to visualize it like there is with regular languages. Did that answer your question?
Yeah.
Other questions? That was a good one. Finally, we need some way to accept. In general, we will continue this process for each production, but there were only those three in this example. After you finish all of the productions, we need one final transition to an accepting state that we make if the stack is empty. So that would look like this. We basically want to say, if we're in state Q1 and the bottom of the stack character is Z, we want to read no input and make no change, just transition, lambda transition, teleport to a final state. So we will make one more state, final Q2. This transition is on lambda, Z, lambda. No change, only possible if the bottom of the stack symbol. If that's the case, we can just teleport and accept. Questions? Some things to note. Just as Dominic mentioned, all of the processing happens in this middle state. It's difficult to draw and visualize, especially when there's text over the top of it. So there it is on its final form. I'm just gonna leave it here so people can actually see it outside of the text that's over top of it. But yeah, it's kind of gross. It's not particularly easy to visualize what's going on at an abstracted level. You really have to analyze these transitions to understand what this state machine is even doing. I'm free to erase. Everyone have what they need? Okay, one more example. Here's a grammar. First thing to ask, is it in Greibach normal form? At least we should be able to recognize whether or not something is in Greibach normal form, even if we're not going to convert a grammar into Greibach normal form. Is this in Greibach normal form? Every production should start with a terminal and end with some number of non-terminals. 0 or more. So yes, this grammar is in Greibach normal form. Go ahead and take a little bit of time, draw the NPDA that accepts it. From the beginning, you can start asking yourselves questions like, how many states will it have? The question is still 3, just like before. A start state, a parsing state, and a final state.
What's a huge typo on the project?
That is a good question. I was gonna talk a little bit about the project because. Think that will be okay as long as you continue to only use what comes with base Python and don't import any other. Packages to make it too easy.
Yeah, I don't do everything. Which is, yeah, I'm pretty sure basic. Dictionary.
You definitely should be,
Yeah, dictionary,
yeah,
Python, it's all within.
yeah.
Yeah.
And there's nothing special about having access to a dictionary in Python because you have access to maps in Java that come with the language. Did everybody get a chance to look at the project?
Have an extra credit, proposal for it,
What's the,
for reading in the input file. If we write out what the grammar of the input file is.
oh gosh. That is funny. No, there's gonna be plenty of extra credit possible from a second possible project. If people want to implement multiple projects, I'm cool giving extra credit for that, because I think. The more you put in your code portfolio, the better. Thinks they have an MPDA? Approximately one person? Approximately two people,
What did you say?
if people have an NPDA. Some people who would like some more time to work on this. Who wants to come up and draw their solution?
I'll do it.
Okay.
I'll
Yeah.
do it really fast, so I don't do it.
Orange, okay?
Hi, Zoom.
And that's okay,
I'll have to like do this so soon you can see it.
as long as you stay in the whiteboard, the white highlighted portion, that's what I try to zoom in on.
Find an order. Things I'm just gonna get exactly.
Yeah.
what I got.
Absolutely.
Yep.
I see the correct number of transitions. That's good. Is this what other people have? Agreement, disagreement? Looks like we have multiple agreements. Yeah,
Mine's a little different, but
how is it different?
I guess the main thing is, from Q
Oh,
zero to
that's
Q.
wrong, yeah, that's, I missed that.
From Q0 to Q1, I had, it reads an A, pops an S, and pushes an A. And maybe,
So you see the ability to just add the S from Q0 to Q1. So we need to read nothing. We pop the bottom of the stack symbol and push S. I agree with this. So this is just pushing the initial S onto the stack, yeah.
I think there's a typo
Or
on,
error, yeah,
an error on the top left loop back.
yeah, I forgot what I did there.
Yeah, so this represents this rule. Is that the intended rule?
Yeah, I think so,
So yeah, you read a B, you pop an A, and you want to push a B.
yeah, that's what it was.
Yeah. Now do we have agreement? Any other changes?
I have a question.
Yeah.
Like, for the transition from Q1 to Q2, why did that we like get rid of this when we didn't do that for like other things?
Gotcha. So it's like, well, why is the bottom of the stack symbol gone here?
Yeah,
It's because Z is not a legal stack character to push.
okay.
So you could technically have something like lambda. You need to be able to read the Z to say the Z has to be the bottom of stack character. This could be a Z, honestly. I think that's okay.
Maybe I'm missing it. Is there a read or pop big A, read a lambda in, push lambda?
This rule,
Yeah.
I missed that, was that supposed to be my time?
I think that's. No, this is the ABC.
Oh, I might have messed that up.
The top left and the bottom right are the same transitions.
Yeah,
Oh, yeah, so the top left one was supposed to be A lambda,
Yeah,
not B A lambda.
yeah, so we want to
it's all good.
read an A,
You know, this is learning for everyone and.
pop an A,
Push.
push nothing.
I don't think I'm quite understanding the Q0 to Q1, why we have Z at all.
So we always need a bottom of the stack symbol because we need to
Oh.
evaluate something like, we need to do this rule at least once. And to be able to do this rule, it needs to be on the stack.
So why couldn't S be on the bottom?
Because we don't necessarily know that that's the start symbol to start with. We need a process that says begin, I see what you're saying, and I think algorithmically, you could probably skip that step. But technically, we want to start with a defined bottom of stack symbol that represents an empty stack. And then we want to push on the first thing that we want to do, which is resolve S. So it represents kind of the very first step that we need to do, but that the result of that first step will always be that we have the star symbol on the stack and nothing else.
My other question is, will it always be 3 states? Because I'm trying to think of. Like when
It
it's
wasn't
not,
for WWR because we had different methods for this.
okay,
Or there will be different options, just like when you constructed a DFA or an NFA, there were multiple possible DFAs and NFAs. There will be multiple that are possible, but if you're going through and converting a grammar, then it's much more difficult to figure out where those transitions are supposed to come from or where they're supposed to be if they're separate. One fun activity for the next couple days might be to go play around with the WWR, come up with a grammar for it. Find a site that converts it into Greibach normal form for you so that you don't have to worry about the actual transition, and then go write it out and see if it has a single state when you follow this algorithm, a single parsing state, or whether you can see it with two. Try to get that together in your head to see what is the difference between having a single parsing state and two different parsing states. That would be a fun, not so fun project, but it might reveal some fun, interesting things about grammars. And non-deterministic push down automata. Good question, though. Anything else? All right, I like it. I like it a lot. Any other questions about the diagram? Are we good to erase it? Everyone have what they need? All right, thank you, Mike. I just have answers here for people who are coming back and doing this later so that you can. You can come back and actually see the results here, so you don't have to go back to the image and go back to the lecture video. Just like we can convert from a grammar to an automata, we can also convert from an automata to a grammar. This is not something that we're going to go into depth about because I just don't think that we have time, and it's not terribly different. You're basically just simulating the grammar productions from the NPDA, so it's kind of the same process, but in reverse. So I think that if you intuitively understand one, the other process is understandable, which is why I feel more okay not doing a ton on this. Basically, the stack is going to represent all non-terminals that haven't been expanded yet. We'll make two important assumptions. There's a single final state in the NPDA. That's kind of important, that we can only enter if the stack is empty. That's necessary for the grammar's purpose. There will always be a case where the NPDA can be represented like this, even if it's possible to represent an NPDA with multiple final states. If we make this assumption, then this algorithm will be much easier. And each move will either increase or decrease the stack count by 1. So it's not quite synonymous with Greibach normal form, where we had multiple non-terminals in each production, but you can have an equivalent grammar that's kind of in Greibach normal form light, which is what you'll be producing, that has up to 1 terminal and a single non-terminal, which creates a really long, unnecessarily long grammar. So you may need to simplify the grammar after you're finished with it. So any existing NPDA can be restructured such that these assumptions are met. We're not going to go into the exact process. I won't ask you homework questions about it. I won't ask you exam questions about it. Yeah.
So unlike what we just did from CFD to NPDA, we're not gonna have things where like the stack doesn't change essentially. It needs to either decrement or increment. Okay.
Yeah. It'll always either increase or decrease by 1. What we haven't covered that we really do want to cover is determinism. Because we've only talked about pushdown automata in a non-deterministic form. And we've only talked about grammars in a non-deterministic form. So determinism in context-free grammars is actually really important, but it turns out to be a subclass of context-free grammars and non-deterministic pushdown automata. So we'll start with just a fun question. What restrictions do we need to place on a non-deterministic pushdown automata to turn it into a deterministic pushdown automata?
Something about lambdas, like maybe can't like just.
Yep, we cannot transition without consuming an input character.
Yeah.
Yep. What else do we think we need to do?
You must not have multiple transitions out of the same state using the same character and stack symbol.
Yes, if it's a distinct input character or input character and stack symbol, then there can only be one transition associated with it. Whereas in an NPDA, there could be any number of them, and we just simulate them in parallel. And it also still needs to be a total function. So for every possible input character stack symbol pair, we need to have some transition defined that may lead to a trap state, but that trap state's gonna be really gnarly to make now because we have every possible transition to that trap state for every possible input character, stack character pair. So at most, one move can be made for a given input symbol in stack top. A lambda transition is possible for a particular configuration. No alternative that does consume an input character is available. So we can teleport, but only if that's the only thing we can do there. We can't also consume an input character. So why are lambda transitions still allowed? And the reason is we can not consume an input character and make a change to the top of the stack, and it is doing something. So it's not truly a teleport, it's just moving states without consuming input characters, but still manipulating the stack, which is a transition. So you just can't have double lambdas where we don't consume an input character and don't make a change to the stack. That's the real lambda in a context-free environment.
So with the other rule that you just had, so this would essentially kind of just mean like. We need to put a non-terminal in the stack if we're gonna like do something.
Yeah, you
like
need to
this.
push or pop from the stack if you're going to make a lambda transition between states. And if you're gonna make a no-op between the stack, then you need to change the state that you're in. You need to move from, Q1 to Q2 or something of the sort, if you're doing a no-op to the stack.
Okay.
My favorite way to think about determinism at any possible time, given the current state, when you read an input character, you can only make one possible move with that input character. If you make a deterministic pushdown automata and there's any possible way to make multiple different transitions on reading a particular character with a particular character on top of the stack, then it's not deterministic. So only one move can work. I talked about this briefly, but in regular languages, we can freely convert between determinism and non-determinism with regards to your finite automata. Now, no such conversion exists because they represent different classes of languages, which is interesting. Very, very interesting. Some NPDAs have an equivalent DPDA, but some do not. Let's try to motivate this intuitively to try to understand why these actually represent different classes of languages. I have 1 minute. I'll see if I can at least very briefly go over this, and then we'll start tomorrow's class going over it again. So we have two languages, L1 and L2. We have A to the N, B to the N, which we know is context free. A to the N, B to the 2N. Is this context free? When we see an A, we're just gonna push two things onto the stack. And then when we see a B, we're gonna pop one thing off the stack. And that way we can map the one push, which is two characters, to each pop, which is one character, which means that if we end up with an empty stack, we saw twice as many Bs as we did As. So it's very similar to A to the N, B to the N, except instead of pushing a single A when we see an A, we'll push two As when we see an A, and then pop one A when we see a B. After we transition to reading Bs, which is why we need two states for this, two parsing states. Questions? All right, I'm already out of time, so we'll just come back to this tomorrow. But we'll see that this helps us to understand that an NPDA can exist when we take this union, but a DPDA cannot possibly exist when we take this union. See you tomorrow. Check out the project.